In this system design, we explore how to build a scalable and reliable hotel reservation platform, something akin to what powers Hilton, Marriott, or Booking.com. This system must be capable of handling millions of users simultaneously searching, booking, modifying, and canceling hotel reservations. It also needs to support dynamic pricing, real-time room availability, and secure payment processing. A well-designed hotel reservation system ensures high availability, strong consistency where necessary, especially during booking, and supports business operations such as hotel management, pricing updates, and customer support. We'll begin by defining the core requirements and then gradually dive into the architecture, API design, data modeling, service decomposition, and deep dive into concurrency handling and scalability strategies. The problem is to design a hotel reservation system like Hilton. Here are some good requirement questions to ask. What's the scale of the system? Do customers pay when they make reservations? Can customers cancel reservations? Do we allow overbooking? In this slide, we walk through the high-level design of a hotel reservation system, something akin to Booking.com or Expedia. This system must be robust, highly available, and consistent, as it handles bookings, payments, and real-time room availability. 1. API design. We begin with a well-defined set of RESTful APIs that form the public interface for all client applications, be it web, mobile, or third-party integrations. These APIs cover CRUD operations for hotels, create new hotel records, update location or amenities, or delete obsolete entries. Rooms, add or modify room types, availability, or room-specific attributes. Reservations, fetch available rooms, make a reservation, or cancel an existing booking. These are key for real-time user interactions and must be low latency and idempotent to prevent double booking on retries. 2. Data model. We use a relational database as transactional integrity, ACID properties, is critical, especially when two users try to book the same room. The schema includes hotel and room tables for inventory, guest and reservation tables to track users and bookings, room_type_rate for dynamic pricing for room type and date. 3. Microservices architecture. To ensure scalability and modularity, we break the system into microservices: hotel service for managing hotel data, rate service for dynamic pricing and promotions, reservation service for bookings and availability, payment service for handling transactions securely, hotel management service for back-end admin tools. Each service can scale independently and has its own database to avoid cross-service coupling. 4. CDN. Content Delivery Network. We use a CDN to serve static assets like hotel images and user content quickly across the globe, minimizing latency and offloading traffic from the core system. 5. API Gateway. All client requests are routed through an API gateway, which provides a unified entry point, handles rate limiting, authentication, load balancing, and routes calls to the appropriate microservice. This simplifies client logic and enhances security. This structure ensures the system is scalable, maintainable, and ready to serve both end users and hotel administrators efficiently, even under heavy load. In this slide, we'll dive into the complexities behind reservation logic and system scalability in a hotel reservation platform. Let's begin with the booking model. Guests don't reserve a specific room. Instead, they book a room type like Double Deluxe or King Suite. The actual room assignment is deferred until check-in. To manage this abstraction, we introduce a room_type_inventory table. It's indexed by hotel_ID, room_type_ID, and date, and maintains the total inventory and the number of rooms already reserved. This table is at the core of our availability checks. Now, concurrency is a major concern here. Suppose there's only one deluxe double room left. If 3 users check availability at the same time, they may all get a yes because reads are happening concurrently. To handle such race conditions, We avoid pessimistic locking due to performance bottlenecks under high concurrency. Instead, we prefer optimistic locking. Each update to a row increments a version number. If a transaction finds that the version has changed during its processing, it aborts and retries. This avoids contention while still protecting against overbooking. For consistency and durability, we also rely on database-level constraints to prevent writing invalid states. From a scalability perspective, we shard our database by hotel_ID. This ensures that each hotel's operations are isolated and distributed, allowing horizontal scale-out. We use an LRU, least recently used, cache to speed up access to recent booking and availability data, especially useful for trending or frequently searched hotels. However, cache consistency can be tricky. Changes to availability must be propagated to both the database and cache correctly. This is where techniques like write-through caching or eventual consistency models come into play. For strong consistency across services, e.g., inventory and payment, we may resort to a two-phase commit, 2PC mechanism. Although 2PC can introduce latency and complexity, it's sometimes necessary when atomicity across microservices is critical. In summary, this deep dive touches on the fine balance between consistency, availability, and scalability, and how choosing the right locking, caching, and sharding strategies is key to building a robust hotel reservation backend.